All right, everybody. I guess we can start. Can you all hear me?
Yes, can hear you.
Okay, great. Okay, well, welcome to another Galford seminar. Today, our speaker is Dr. Daniele Michilli, and he'll be speaking on fast radio bursts to probe the circumgalactic and intergalactic media. Daniele Michilli was born in Rome, Italy, where he obtained his master's degree in astrophysics at La Sapienza University. He then moved to the University of Amsterdam to observe and study pulsars and fast radio bursts. After receiving his PhD, Daniele accepted a position at McGill University in Montreal to work with the CHIME telescope. He then received a Banting Fellowship to find and study fast radio bursts with CHIME. Daniele is currently a postdoc at the Massachusetts Institute of Technology. All right, Daniele, you can take it away.
Hi, everybody. Thanks, Shipa. Let me share my screen. Let me say that it's a pleasure to be here with you. In my talk today, I'm going to describe what are fast radio bursts and how we can use them to study the intergalactic media. My talk is broadly divided in 4 parts. Initially, I'm going to give a broad overview of what fast radio bursts are, just to bring everybody up to speed. And if there is any expert in the field, I'm sorry. I hope that this summary will be helpful anyway. I will then discuss the propagation effects that the radio waves emitted by fast radio bursts undergo when they travel the universe, and with a focus on dispersion. And in the third part, I will explain how we can use this dispersion and the other propagation effects to study the intergalactic medium. And in the last part, I will give a practical example of one study that used the dispersion of fast radio bursts to constrain the intergalactic medium, and what are the future prospects for the field. So let's get started. What are fast radio bursts? Well, as the name suggests, it's a burst in the sense that it's a transient signal. We only see it for a short period of time. Fast radio bursts are so far only detected in radio, with one possible exception of a fast radio burst that went off in our own galaxy, where we also detected some X-rays. And it's fast in the sense that typical durations are around a millisecond. The characteristic that distinguishes fast radio bursts from other galactic radio transients is their luminosity. In fact, they are so luminous that we can see them from distant galaxies. If we, for example, plot the luminosity of some radio sources on the vertical axis as a function of their peak frequency and time, we see that the fast radio bursts occupy an otherwise uninhabited space in this diagram, whereas galactic sources such as pulsars and rotating radio transients that happen on similar timescales have luminosities that are orders of magnitude smaller. We have other transients that have comparable luminosity to fast radio bursts, but they have much longer timescales. All of this to say that with these radio luminosities, we can detect fast radio bursts from distant galaxies. And this is an obvious advantage because fast radio bursts are the only sources detected at these timescales coming from so far in the universe, in radio, of course. So in this slide, we see how we usually detect a fast radio burst. There is a telescope that monitors a certain patch of the sky We call this the field of view of the telescope. And it detects the signal coming from this patch of the sky in time. And you see that usually you have random noise variations and variations of everything that is in the signal. But sometimes you have this spike of emission. So what we usually do is we set a threshold for the noise, and we basically just detect anything that varies in time over this threshold. Of course, since fast radio bursts happen randomly all over the sky, if we only sample a very tiny patch of the sky, so our telescope has a very small field of view, we will see very few fast radio bursts. But with a telescope of new generation with a much larger field of view, it's much more probable that by chance one of the fast radio bursts that happen randomly all over the sky, we don't know where they come from, will be in our field of view, and so we can detect it. This is why modern machines built to find fast radio bursts have a much larger field of view and can see a much larger patch of the sky than traditional radio telescopes. And now I want to open a very short parenthesis. In the next couple of slides, I want to speak about the CHIME FRB experiment, which is the project that I'm involved in. CHIME is this radio telescope that you can see in the picture and also in this video. It is formed by these 4 cylinders aligned in the south-north direction. And on top of the cylinders, you can see these stripes that contain more than 1,000 antennas. This cylindrical shape allows CHIME to have a field of view of a long stripe from south to north, so that it can see all the sky in one day as the Earth rotates. And this very large field of view compared to traditional telescopes allows CHIME to detect around 100 fast radio bursts every month, which is basically the same amount as discovered by all the other telescopes ever. We just published a catalog with the first 500 fast radio bursts to study the properties of the population. And here you can see a comparison in these plots. This is the top one are the fast radio bursts in declination and right ascension before CHIME, and the bottom is the catalog of the first 500 fast radio bursts discovered by CHIME. So we are really revolutioning the field of understanding how fast radio bursts work. Now I want to jump to the second part of the talk, discussing how the radio waves propagate in the interstellar and intergalactic media. But before that, I wanted to ask if there is any question so far on this fast radio burst summary. Okay, if there is no question, then let's discuss about the propagation effects. In this slide, I showed you how this typically a telescope, a radio telescope, discovers fast radio burst and any other transient source. This is, of course, a simplification of real life, and the first simplification here is that usually you don't see all the signal together, but the telescope receiver is divided into frequency channels. So with a radio telescope, we monitor every frequency subband independently. And if you see a bright radio signal, it will look like this. At first, it will appear at higher frequencies, and then you will see at lower frequencies, and lower frequencies still delayed, and so on and so forth. And this is a very well-known effect called dispersion. The dispersion causes the signal to have this delay, which is dependent on the frequency, accordingly to this formula here, and the constant of proportionality, which determines this sweep, it's called dispersion measure. The dispersion is due to the interaction of the radio waves with plasma, with free electrons in the media that it travels. And these free electrons slow down the velocity of the radio waves in a way that lower frequencies are slowed down more, so they arrive later at the observer, even if they were emitted all at the same time. The dispersion measure, we see it's basically the integrated column density of the electrons. So it's Ne is the electron number density, and L here is the distance. So all of this is to say that with fast radio burst, if we know the distance, we can measure the electron column density along the line of sight. This is a real-life example. Actually, this is the plot in the first paper where a fast radio burst was first reported in 2007. You can see in the background what is called the waterfall, which is basically the intensity of the signal as a function of frequency and time. This is similar to what I showed here, but instead of plotting the peak, the signal intensity as peaks, they color-coded, so white is a brighter signal. And we can immediately see that, well, there is this horizontal stripe. This is only human-generated interference. And then there is this dispersed signal, very similar to what I plotted before. And this is actually the fast radio burst. Now, if we correct for this dispersion, we know mathematically how it works. We correct it and we straighten it up via software, and then we sum all the frequency channels together, we obtain this inset, which is the so-called pulse profile of the fast radio burst, which is basically what I was showing a few slides back. This is the pulse profile. Now, the interesting part for a fast radio burst is that this delay, as I said in the last slide, is caused by the free electrons in the Milky Way. By the free electrons along the line of sight. But if we only take the free electrons that are expected to be in the Milky Way, they can only account for this much of a delay in the green part. So the red part actually comes from electrons beyond the Milky Way. So there are part of them is in the host galaxy of the fast radio burst, and the rest is in the medium in between galaxies, the so-called intergalactic medium. Now, dispersion is not the only effect that we see in fast radio burst. There are others. I don't have much time to cover them, and they are a bit more complicated, so I will give you just a very quick hint of two additional effects that we can use to study the medium. The first one is scattering, which is due to the turbulences in the medium. You can see here they are schematized as these blobs. So instead of having like continuous plasma, you have clouds of plasma, and when the radio waves bounce from one to another, they get delayed. And this causes this exponential tail in the signal, in the peaks of the fast radio burst, which is called a scattering tail. And as you can see in this plot from another fast radio burst discovered by Thornton in 2013, you can see that this is frequency dependent. So basically what they did is divide this waterfall in 3 parts and plot the pulse profile separately. And you see that at lower frequency, the scattering is larger. And we can use this scattering timescale to see how turbulent the plasma is. And another example of a propagation effect that is very useful is the Faraday rotation. Faraday rotation is a rotation of the polarization vector of the radio wave that is due to magnetic fields in the plasma. So since there are magnetic fields parallel to the propagation of the radio waves, this polarization vector is rotated, and we can detect it if we project it on the sides. We can detect it as these oscillations of the signal along the frequency. And from the amount of these oscillations, we can reconstruct what is the magnetic fields in the plasma parallel to the propagation of the radio waves. Now, I will not go in further details on this because the time is limited, but for people interested, these are additional possibilities. This was a bit of an intense part, I think. So if you have any question, please ask them.
Danielle, there are a few questions in the chat from Paul Fallon. How precise is CHIME in determining the FRB position?
That's a very good question that I'm going to discuss in more detail later, but to give you a quick answer now, CHIME is not very good to localize fast radio bursts, and this is because it's a compact array. So the localization precision depends basically on the size of the telescope, and CHIME is a big telescope, but not so big. And yeah, so let me discuss this in more details in the next part.
Okay, thanks. And another question from Sriram. How well constrained is the model for the Milky Way CGM contribution, and how does this behave as a function of position?
Let's see, the interstellar medium of the Milky Way is pretty well modeled thanks to pulsars and other galactic radio transients. However, it gets uncertain near the edges of the galaxy because, of course, you don't have many sources there, and so you need to extrapolate. And the farther you go, the more uncertain it gets. So the halo surrounding the Milky Way is very uncertain. We don't know how much plasma is there exactly and how much it contributes to the dispersion measure. One study that we're trying to do at CHIME, we are preparing it. A student, Amanda Cook, is working on this, is to get the nearest fast radio burst that we can and the farthest pulsars that we can, and study what is the difference in dispersion measure of the two, to study what's the amount of plasma in between them.
Okay, thank you. Yeah, we can move on with the talk.
Sure. So let's see how we can use these propagation effects, and in particular the dispersion, to study the medium. Well, we've seen the mathematical function of this dispersion measure is pretty simple. We can directly measure the dispersion measure from the waterfall, and we can assume that there is an average electron density, and in this case, the dispersion measure is just given by, broadly speaking, by the the average electron number density times the distance of the source. So we can use the dispersion measure as a proxy for the distance if we know the average electron number well enough. As I mentioned before, this is something that is commonly done for galactic sources, in particular radio pulsars, which are these neutron stars that rotate and emit beamed radio emission, so that for each rotation we see one emission from the neutron star. We measure the dispersion measure. If we know their distance through other means, for example, if they are close by, we can obtain the parallactic angle, or if they are in globular clusters, we know the distance of the cluster, and so on. We have an independent estimate for the distance, and so now we know dispersion measure and distance, and we can obtain this average electron density. And that is basically the way in which we construct these models of the electron density in the interstellar medium. Now, with fast radio bursts, of course, we can do something similar. We can, if we know their distance, we measure the dispersion measure, and we could obtain this electron density. So how do we measure the distance for a fast radio burst? Well, one way is to measure the redshift of the host galaxies. However, to measure the redshift of a host galaxy, we need to know exactly where this fast radio burst come from. So this is not an easy task. This is challenging because the angular resolution of a radio telescope is proportional to its wavelength over the telescope size. Localizing a fast radio burst to a galaxy is not an easy task. If we take the beam size of FAST, the largest single dish telescope in the world, you will see that at this like big red circle, and it contains a huge number of galaxies. So even if we detect a fast radio burst with this FAST telescope, we don't know where it will be in this region. It could be any of these galaxies. To localize a fast radio burst, we need something with a resolution of around 1 arc-second for most fast radio bursts. Of course, the farthest is the galaxy, the smaller this diameter must be. And from this formula, we see that to localize a typical fast radio burst at 1 gigahertz at a redshift of 1, we need a beam to get a beam size of 1 arc-second, we need a telescope size of more than 60 kilometers. And it is, of course, not possible to build a single telescope of 60 kilometers. So what we do, we build arrays of telescopes, and we connect them, and the the longest baseline between the elements of the telescope will determine the beam size. In the image, for example, is an example of VLBI, where a telescope in the US, well, in Puerto Rico, Arecibo, was connected to many telescopes in Europe, and they work together to localize one fast radio burst to a single galaxy. In summary, we measure the dispersion measure from this waterfall. Then we localize the fast radio burst to a host galaxy thanks to arrays of telescope like the VLBI. Now we have the galaxy. We can observe with optical telescopes, and we measure a redshift from the spectrum of the galaxy. And from the redshift, we obtain the distance. Now we have the distance in the dispersion measure, and we calculate the average electron density, which is what we are after. One step further, the average electron density for a fast radio burst is not so interesting because it's formed by the average electron density of the Milky Way, the host galaxy, and the intergalactic medium. What we really want to measure with fast radio burst is the intergalactic medium. So we need to subtract the other two quantities. For the Milky Way is not so challenging because, as I was saying before, this number here is reasonably well known, even though there are some uncertainties especially at the edge of the Milky Way. This is pretty well constrained. The host galaxy is much more tricky, and this is because the host galaxies, not only we cannot measure this number directly, but also host galaxies are of very different types. We have found fast radio bursts in spirals, in irregulars, in elliptical, basically in every galaxy that you can imagine. And therefore, the plasma in these galaxies vary a lot. And it's also very difficult to model. We don't know the condition of every single galaxy, of course. So what we usually do is try to detect a large number of fast radio bursts. So this number will have a large uncertainty, but with a large number of fast radio bursts, we can study statistically. We know that there is uncertainty, but hopefully the number will oscillate around some central value. And finally, we subtract these two from the average electron density, and we can finally obtain the intergalactic electron density. So this is, we are entering in the last part where I want to show a practical application of all of what I've talked about until now. So any further questions?
We have a question in the chat from Sriram. What about effects of foreground galaxies?
Yeah, another very good question. So there are, well, two ways to answer this. First one is, if we identify that there is a foreground galaxy, this may be very good because we can study the interstellar medium of the foreground galaxy. This has been done partially. There was a fast radio burst that came close to a galaxy, so it was possible to constrain the halo around this galaxy. However, this is also a limiting factor because it will increase the dispersion measure significantly, and also the scattering. It will be a fast radio burst with a foreground galaxy will be both more difficult to detect and also more difficult to study. But luckily for us, there are not many cases. I mean, the chance coincidence at redshift 1 of having a foreground galaxy is limited. So there will be a few outliers in the distribution and, of the dispersion measure, and we will know that they are probably from a foreground galaxy or from a very extreme environment around the fast radio burst. Okay, if there are no further questions, let's go for the last part of the talk. And now there are a few examples already of how we can use fast radio burst to study the intergalactic medium. But I want to focus on one, which in my opinion summarizes the power of this tool. And it's a study of the missing baryons. Now I'll talk in a couple of slides of what this means, but in the meantime, I want to show you this telescope that probably many of you are already familiar with, which is called ASCAP. It's a telescope in Australia and is one of the precursor of SKA. It, as you can see, it has a concept very different than CHIME. There are 36 antennas of 12 meters each, and they are put on this field so that the maximum baseline is around 6 kilometers. And here you can see a closer picture of single antennas, and you can see that there are like antennas that are farther away. And all these antennas are connected together to form beams on the sky that is to monitor different patches of the sky at the same time. Since the baseline is larger than CHIME, it can localize sources much better. So this telescope is not discovering as many fast radio bursts as CHIME, but each of the fast radio bursts that is discovered can be localized very precisely. Therefore, they already presented 9 localization of fast radio bursts that you can see here in the plots. The localization region is plotted with an ellipse, either white or black, and the background color is an optical image of the galaxy. As a parenthesis, it's interesting to notice that most of this localization happen in the outskirts of the galaxies, which probably tells us something about the origin of this fast radio burst. For example, they likely are not AGNs, since they are mostly found at the center of galaxies. But for the purpose of this talk, more interesting is the fact that now we can measure a redshift, so a distance for each one of these fast radio bursts. In their study, they used 5 of these fast radio bursts plus 3 that were localized by other telescopes. That you can see in this plot. Now, in this plot, all the symbols are fast radio burst, and on the horizontal axis you can see the redshift, so the distance of the fast radio burst. On the vertical axis is the dispersion measure of a cosmic origin. So it's basically this electron density intergalactic, or in other words, is the dispersion measure that these intergalactic electrons will cause. Now, in in cosmology, there is this missing baryons problem, which is due to the fact that from simulations of the evolution of the universe, we expect a certain number of baryons in the local universe. But if we observe other galaxies, we don't see as many baryons as expected. And this is called the missing baryon problem. And leading theories predict that these baryons that are missing are actually in the intergalactic medium. This black line is a simulation of what would happen if indeed the missing baryons are in the intergalactic medium, how much they will contribute to the dispersion measure of fast radio burst. So this is not a fit, it's from simulations. And the gray area is the uncertainty on this simulation. And it's incredible to see that even if with all the large uncertainties, fast radio burst trace very well this black line. So this is the first confirmation from fast radio burst that the leading theories are correct and that the missing baryons are indeed in the intergalactic medium. And I want to highlight the power of fast radio burst because this important result was only obtained with 8 fast radio bursts, which in my opinion is very impressive. Now, let's imagine what we could do with hundreds or thousands of fast radio bursts localized to single galaxies instead of 8. For example, we could select them based on their position on the sky. And this is something that was recently done by Connor and Ravi, where they select fast radio bursts near near cluster of galaxies. And even if the fast radio bursts were not very well localized, they were able to put a constraint on the dispersion measure of cluster of galaxies. Unfortunately, I don't have much time to go into detail there, but this is another example of application. So with thousands of localized fast radio bursts, we could study the profile, the density profile of the intergalactic medium. We could use the other propagation effects, such as Faraday rotation that I mentioned before, to study the magnetic fields of the intergalactic medium, which are basically unknown. We could study the interstellar medium in other galaxies, which is also basically unknown. For example, we could select fast radio bursts near or behind the GNs and study their local environment. So there are like an unlimited number of possibilities there, and we are just scraping the surface of what is possible to do with fast radio burst. The limitation and the challenge here is that we need a telescope that finds and localizes thousands of fast radio bursts. This is what I want to talk about in my last slide, which is a project ongoing that is called CHIME Outriggers. Now, we have this CHIME telescope that is very good at finding fast radio bursts. It can find around 1,000 fast radio bursts every year, but it's not very good at localizing them. And this is because, as I explained before, it's a compact array. What we are doing is building other smaller version of CHIME across North America at baselines of around 3,000 kilometers. And these smaller CHIME telescopes will look at the same position as CHIME. And these smaller telescopes are called Outriggers. Looking at the same position and connecting them together, we now have a telescope with a baseline of 3,000 kilometers. So every single fast radio burst that is detected by CHIME can be localized to a single galaxy And with this, with 3,000 kilometers, not only it was a single galaxy, but where we will know where the fast radio burst is inside the galaxy. So this will open up incredible possibilities for the field. And we expect to localize around 1,000 fast radio bursts per year. And this project is ongoing, as I was saying. The construction's already started, and we expect that by the end of next year, all of the other Outriggers should be completed or in way of competition. So stay tuned, because I think that the fast radio burst field in the next years will have a huge jump. And yeah, this concludes my talk, and thank you for your attention.
Thank you, Danielle. That was really interesting. If anybody has questions, please put them in the chat, or if you prefer to ask them out loud, you could even just put up your hand and ask them like that. Oh, there we go. We have one. Okay, Yenzi, can ask your question.
Hello, am I audible? Hello?
Yes, yeah. We can hear you.
Hello?
We can hear you.
Okay, good. Yeah. So yeah, thank you for the very nice talk. And you mentioned about localization of FRB with these Outriggers, etc. I mean, certainly the longer baseline will improve the angular resolution. But I wonder what optical survey that you have to prepare in order to match it up. You know, I don't think with radio only that you are able to just identify where it really is locally. I think you need some optical survey to match it up, right? So can you elaborate on that? Thank you.
Absolutely. This is another challenge. With radio, we can know exactly which galaxy it comes from, because we basically have images of all the sky with optical surveys, but we don't have spectra for every single galaxy. So we basically need optical spectra to obtain a redshift of the galaxy. Our plan for now is using catalogs that are already in place that monitor a large part of the galaxies. And if there is a galaxy where we don't have enough data, we will obtain new spectrum. We are also partnership with some optical telescopes to obtain this spectra quickly, but this is still, something ongoing. So we hope to have something better in the future, where if we need a galaxy spectra, we can obtain it quickly.
All right, Paul, can I ask a question?
Okay, hopefully you can hear me.
Yeah.
Yeah, I think first I wanted to say thank you. I thought it was an interesting talk, and I learned a lot from it. But I was just going to ask, I know you haven't touched on it, but are you able to say much about what is known at the moment around sources or potential sources of fast radio bursts?
Yeah, absolutely. I intentionally skipped that part because it will be another 45 minutes talk. Well, there are many theories about fast radio bursts. Before CHIME released the catalog, the internal joke was that there were more theories than actual fast radio bursts. And now the situation has changed, but we know that at least some of the fast radio bursts are due to magnetars, which are neutron stars, pulsars, but with very high magnetic fields. And we know this because we have detected one in our galaxy, and it was originated from a magnetar. In other galaxies, our instruments are not sensitive enough to detect magnetars, so we don't know if all the fast radio bursts come from magnetars. And this is also because the luminosity of fast radio burst is a huge variation. It spans 10 orders of magnitude, and our models are uncertain whether a magnetar can produce all the fast radio bursts that we see, even the most powerful. Other theories include merger of neutron stars, include explosion of neutron stars, black holes, and yeah, all sorts of things. I hope this clarified a bit the subject.
Oh, that does. Thank you.
Thank you.
Cool. Thanks. Sriram, can I ask a question?
Hi, thanks for a great talk. FRBs has been a concept of fascination for a while for me. I wanted to ask if when we find an FRB and we model the electron column density along the line of sight, do we account for foreground clusters or galaxy groups or any of such things in the modeling?
Well, with a single fast radio burst, we cannot, because our models are not accurate enough to know the variation of the electrons in the intergalactic medium and around clusters and things like this. This is what we hope to do if we detect thousands of fast radio bursts, is to improve the models. So since our models are not accurate enough, we want to detect 1,000 fast radio bursts and build a new model that will be much more accurate than what we have now.
So there has not been a case where we have pierced a cluster halo and detected the ICM or anything of that sort?
Not really. It's a bit difficult because you have all these other quantities that are uncertainty. You don't know the local contribution from the environment of the fast radio burst. You don't know the local ISM, and so you cannot measure precisely one of the electron densities without knowing the others, if that makes sense.
Yeah.
And so I was mentioning this recent study by Connor and Ravi. What they did is using a number of fast radio bursts and trying to do exactly this, trying to see the excess dispersion measure around clusters with respect to places where you don't have big clusters. But this was a statistical study with poorly localized fast radio bursts. So we can improve a lot of the results if we localize the fast radio burst properly.
Awesome. Looking forward to future studies in that case.
Yeah, we both.
Oh, another question from Paul. Yeah, go ahead.
Thank you. Just going to ask something that's also a slightly different topic, but on FRBs that are seen to be repeating. I've heard one or two comments that they've picked up FRBs that might be repeat FRBs. I don't know if you can say much on that. And then on the ones that they have observed, do you know if they're able to show that the dispersion measure is the same on the repeating FRBs?
Yes. Yeah, absolutely. Okay, so we have seen a few fast radio bursts to repeat. So basically they emit multiple bursts coming from the same location and with similar dispersion measure. And they represent about 10% of the fast radio bursts we know, a bit less maybe. For other fast radio bursts, we don't know if they repeat on longer timescales, like every 10 years, we will probably never know. Or if there are two classes of fast radio bursts, some that are repeat, or some others that maybe are due to explosion of stars, so they cannot repeat. we have a couple of repeaters that have been known for years, and we follow their dispersion measure. And surprisingly, we've seen that for one of them, the dispersion measure is increasing slowly. So about, 2 parts per cubic centimeter per year, which means that that it's definitely increasing, but slowly. And this is surprising because we thought, the dispersion measure from our galaxy, the local galaxy, and the IGM, we expect that is constant. So this must be due from local environment of the fast radio burst. And naively, we would have expected a dispersion measure to decrease. For example, if you have a nebula surrounding the material, in time this nebula gets less dense, and so the dispersion measure should decrease. The fact that it increases has been discussed pretty extensively in the literature, and we are not completely certain of why. Maybe there is some reionization in the material around the fast radio burst because there is some, very powerful emission. Yeah.
Oh, thank you. That was fascinating. I wasn't aware that there was a repeating FRB that had a change in dispersion measure. So,
yeah.
Okay, thank you for the information. Really is fascinating.
Yeah, I think so.
Yenju, you can ask your question.
Hello, yes, am I audible?
Yeah. I can hear you.
Hello, am I audible?
Yes, you are. We can hear you.
Okay, good, yeah. Okay, yeah. I wonder, do you know any kind of confirmed FRB that has really large magnetic field? Like for any of these FRB, can we kind of know their magnetic environment in that sense? Yeah, thank you.
Yeah, there is one that is also a repeater, and it was found an extreme rotation measure, one of the highest ever measured in our universe, of something like 100,000 radians per square meters, and this means that locally the magnetic fields are very intense. The issue there is knowing how intense exactly. We cannot know for sure, but we can place some constraint. And the reason why we cannot know for sure is that again that it's difficult to measure the plasma locally. You don't know how much plasma there is locally, because to know that you need to remove the plasma that is in the intergalactic medium and in the host galaxy, and we don't know these quantities very well, so we don't know very precisely what is the contribution of the local plasma. Say that I don't remember on top of my head the exact limit on the magnetic field that we placed around the source of fast radio burst, but was already pretty high as a lower limit. It was, I think, slightly higher than what we find in young supernova remnants and things like this, but it's probably much higher. It's just that we cannot constrain it yet. I hope that
yeah.
well, please.
Yeah, that's very interesting. Thank you very much. And can I send you an email to inquire more on these things? Yeah.
Oh, I'd be happy. I'd be happy to.
Could you perhaps provide your email address in the chat,
yeah,
or if you have it on one of the slides, that would be great.
Sure. I actually cannot write on the chat while I'm sharing the screen, I think. But
okay.
if you Google me, if you Google my surname, my email will appear, or just download one of my papers.
Okay, great. So
thank you very much.
No worries.
if there are no more questions, then I think you can just thank Danielle one more time. That was a really great introduction to FRBs, and that was a very exciting outlook into the future with CHIME and the Outriggers.
My pleasure.
So yeah, thanks again. And then just one quick announcement. So we're all booked up for the rest of the year, but if anybody has any suggestions about any speakers you'd like to hear for next year's Galford seminars, then please do contact us. All right, thanks everyone, and we'll see you next time.
Thank you. Thank you.